Does it make sense? Okay, so this is a parabolic equations. And to analyze the behavior of the parabolic equations, let's introduce a little bit of Fourier analysis. So how much of you have done Fourier analysis before? Okay, about half of the class. Now Fourier analysis is nothing but a decomposing of our W, okay, which is a function of x and t, into a summation of different sine waves. All right, okay, and the way to express sine waves, I mean, one way to express sine waves is exponential functions with imaginary variables. But since a lot of us hasn't done Fourier analysis before, so let's just use sine and cosine waves to make it a little bit easier. So let's say AI times cosine of, let's see, 2 pi times I. Let's actually call it K because K is frequently used to index wavelengths. So 2 pi k times x. So this term is a cosine function with a period of what? With a period of 2 pi 1 over k. Yes, right. Okay. So basically, the larger the k is, the smaller the wavelength, the period is. So the smaller the wavelength is, and the more oscillatory the function is. Similar, we have a bk times sine of 2 pi kx, right? Similarly, that one also has a period of 1 over k. So it just have a different phase. I mean, if you use the Fourier analysis, you make just combine them and use a single complex function to represent both, right? E to the I 2 pi ikx. Okay. And here, I have represented the variation in x using all of these k's. So k goes from 0 up to infinity. So basically, I can represent all types of variations. It's a decomposition of the function in terms of how fast the component would vary in space. But I have not represented time yet. So the time for any t, you have a function of space only, right? If you fix the time, you have a function of space, and you can decompose that function into Fourier series. But the decomposition coefficients may be different for different time, and that is expressed in here. So the coefficients of this Fourier series would be a function of time. So why are we doing this? We are doing this because the Fourier series is extremely benign to performing spatial derivatives. If you have a sine and cosine functions, if you take a derivative, it's still either sine or cosine functions. If you take a second derivative, it's still going to be either sine or cosine functions, right? You can take as many derivatives as you want. You are still going to be remaining sine and cosine functions. And furthermore, the period of the sine and cosine functions wouldn't change if you take a derivative, take two derivatives, etc. All right, so that's extremely good in studying partial differential equations. And so that's kind of the motivating factor of why people actually use Fourier series in a lot of the analytical methods for partial differential equations. So here, for example, if you look at the second derivative, what is it? What is the second derivative of a cosine? So let's say, what is the second derivative of cosine ax? Minus a squared times cosine of ax, right? Okay, so here my a is 2 pi k and 2 pi k, right? So if you do sine of ax double prime is also equal to the same thing, just a polar minus a squared out of it. So that means the second derivative of w but here I have a minus 2 pi k squared times ak of t times cosine of 2 pi kx. And again, minus 2 pi k squared times bk of t times sine of 2 pi kx. Right? Okay, so now let's plug this into the partial differential equation. Plug into the partial differential equation, we have partial w partial t equal to kappa times second order derivative of w. And let's plug this in, right? It's equal to kappa times the whole thing. So let's just plug this in. And furthermore, the time derivative of w, while w being expanded in the Fourier series, can also be analyzed. So if you take time derivative of the infinite series, what is it? What is the time derivative of cosine 2 pi kx? It's 0, right? So all the components of the Fourier series, the cosine and sine functions doesn't change. The only thing that changes is the coefficient. So here's another motivation of doing the Fourier series. It separates the space and time components when you're taking the derivatives. When you're taking the spatial derivative, you only need to care about the sines and cosines. When you take the time derivative, you only need to care about the a's and b's. So you take the time derivative, you get summation k equal to 0 to infinity. Now I have ordinary derivative because a's and b's are just a function of time. Plus dbk dt sine of 2 pi kx, right? So okay, so here if you match the term over here and the term beneath, so let me just copy a little bit, minus 2 pi k squared times ak of t cosine 2 pi kx minus the corresponding sine entry. So this has to equal to this. Okay, and if you've done Fourier series, you know that the Fourier series has to, if you have two Fourier series equal to each other, the corresponding terms has to equal to each other. If you haven't done Fourier series, just imagine you have a series with different frequencies embedded in one function, another frequency. The corresponding frequency has to match because you cannot compose one frequency with the linear summation of different frequencies, right? You can never actually get to the sine. You can never construct a sine wave out of sine waves of different frequencies, right? So basically the corresponding term has to match, which means, let me circle them. This multiplied with kappa has to equal to this for each corresponding k. And the end result is a differential equation that no longer involves x, right? It's a differential equation that only has derivative in t. So what is that kind of differential equation? It's an ordinary differential equation that only has one independent variable. So no matter analytical methods or numerical methods we're going to study later, a lot of the goal is to reduce a partial differential equation into an ordinary differential equation. And we assume we already know how to solve ordinary differential equations, either analytically or numerically. Okay? So basically, if you look at a PDE and say, oh, I have reduced it into an ODE, great job, I'm done. So here, I have an ordinary differential equation, dA dt equal to minus kappa times 2 pi k squared times a. Do we know how to solve that equation? Well, how many of you know how to solve that equation? Oh yeah, I hope most of us know, right? Because that's basically I think it's the first equation they teach you how to solve in ODEs, right? So if you have done any OD, you should be able to know how to solve that equation. So can somebody tell me what's the behavior of that equation?